Good morning and welcome to FUSION22. It is fantastic to see so many of you here in person in London. And a special hello to our virtual audience as well, wherever you're watching around the world. Please do tell us where you're watching from using the chat function on the app and browser. I'm Valerie Jimison, Development Manager for the Fusion Cluster. And the cluster brings together the fusion energy companies, the supply chain, academia, policymakers, investors, and the national facilities. Basically, everyone who is keen to get to fusion faster. So we're here today to showcase the incredible developments and progress that is being made in fusion around the world. And to kick off the day, it gives me great pleasure in introducing Tim Bestwick, Chief Technology Officer at the UK Atomic Energy Authority. Tim Bestwick.
Thank you, Valerie, and let me just echo that welcome, a warm welcome to all of you joining online across the world, and of course a welcome to you here in the Science Museum in London. It's really great to see everybody joining us today to talk about fusion. I don't need to remind you of the need for secure, low-carbon energy, and I don't need to remind you because it's never far from the headlines. We see it practically every day in some form, and I also don't need to remind you because climate change is entering our own personal experience of living. Our high-carbon energy systems are affecting the climate in a way which is impinging on our everyday lives. And in a moment, Professor Mark Maslin is going to talk to us about just that, climate change, which is such an important driver for fusion. Fusion is hugely exciting and holds tremendous opportunity as a low-carbon, secure source of energy. But it's difficult. If you're in the field, I don't really need to tell you that. There are a number of important challenges that we still have to overcome to deliver it. And of course, with that tremendous opportunity for a new major energy source, there's also an incredibly large economic opportunity that goes with that. The global fusion community has been working in fusion research for decades and made fantastic progress, but there are significant technical hurdles that we still have to overcome to deliver this. Progress in the field is accelerating, not least because there's a tremendous amount of activity at an increasing rate, and great progress is being made. And we're going to hear about some of that in our session here this morning. And I think the world is becoming a bit impatient for us to deliver fusion because really the necessity, the imperative has never been clearer. So here we are at FUSION22 to discuss those challenges. And we're going to talk about all the different aspects of those challenges that we need together to deliver fusion. I hope you find it useful, maybe even inspiring, but above all else, I hope that this event helps galvanize us because the world needs fusion energy. So it's my great pleasure now to introduce Mark Maslin from UCL.
Thanks, Tim. Good morning, and I have to say I am the warm-up act. I am the one reason you are here to try and actually inspire you. If I can have my slides up, that would be helpful. Yes, so again, climate change. Tim has mentioned this. I'm going to go through why it's such a huge challenge, what the energy challenge is, and why fusion is absolutely essential for the future, and why, like Tim, I'm really impatient. Hurry up. Okay? So think about it. We have just been through a huge pandemic where we have all worried about sort of flattening the curve, making sure infection rates. And I love this cartoon because what it says is that this was a minor crisis compared with climate change that is coming in the future, or in many places already here. Think about the 40-degree summer we had in London. So, guess what? The science of climate change is even older than fusion. Okay, so 150 years ago, Eunice Foote, she, American scientist and feminist and activist, showed the greenhouse effect. Very simply, she took two test tubes, filled one with air, one with CO2, put thermometers in them, sealed them up, stuck them out in the sun, recorded, and strangely enough, guess what? The CO2 one warmed up quicker, stayed hotter, and then cooled down slower. The greenhouse effect was discovered, and then 5 years later, here at the Royal Institution in London, John Tyndall, with his thermocouple, actually was able to measure it and worked out that water vapor, followed by CO2 and methane, were the most important greenhouse gases. So what is climate change? Because it sounds like it's really complicated, and I feel a bit like Brian Cox saying, well, it's simple physics. It really is. Sun's energy is mainly in the light field, okay? And it falls on the Earth. A third of it reflects back into space. 2/3 is absorbed by the Earth. Now just imagine you're not here in a suit and tie. You're on a tropical island with your favorite cocktail. Mine's a mojito. Think of yours, okay? Now, the interesting thing is you lie in the sunshine and you feel hot. Why? Because that light energy converts to heat. You radiate the heat away, same as the Earth. And that heat goes into the atmosphere, and this is the magic of greenhouse gases. They capture some of that heat. They basically vibrate. They keep that heat for a little bit. They basically radiate it back out. If you took all the greenhouse gases out of the atmosphere, the temperature of the Earth would drop by 35 degrees Celsius. So that would make an English summer, let's be generous, about -15, and an English winter about -35. So greenhouse gases, good. And of course, in 1938, Guy Callender, who actually worked for the British Coal Board, noticed with his temperature records from around the world, 147 of them, that there was an increase in temperature. He had some CO2 measurements done by colleagues, and he already put together that burning coal was putting CO2 in the atmosphere, was warming the planet. Now, CO2 levels have been going up. We've increased our CO2 levels by about 50% compared with pre-industrial times. And as a paleoclimatologist, I can tell you that's probably the highest level for the last 3 million years, if not longer. They are the Keeling curve, just seems to keep going up. Now, let's do a bit of a poll, okay? So come on, you can relax a bit now, because this is just climate change. This is just the fate of the planet, okay? So how many of you actually like skiing and snowboarding? Please put your hands up. Oh my God, you're so much better than my undergraduates. Thank you. Okay, guess what? You better do it quick, because since 1960, Northern Hemisphere snow cover has been dropping markedly. Summer sea ice extent, we basically know that's been melting. And the one that I worry about as a scientist, and as many of you as physicists will, is of course the average heat content of the upper ocean. Why? Well, water has a slow thermal inertia. It covers 70% of the world's surface, and it's 1,000 meters of depth. That's a lot of heat. So that's the one I'm most worried about. Sea level creeping up at 3 millimeters. It's now gone up to 5 millimeters per year, has increased by 24 centimeters in the last 100 years. And then you have the temperature curve, okay? So the warmest years on record up to now is 2020 and 2016 that are tied for that record. But again, most of us, and particularly the public, don't understand the wiggly lines. And so therefore, brilliant colleague of mine, Ed Hawkins, invented the warming stripes. Let's just change them into nice colored stripes. So this is England temperature in warming stripes. As you can see, blue on the left in the 1850s, all the way to dark red in the right-hand side. Now I have to let you into a little secret. This has become a little bit of a cottage industry. So of course you can have a tie. I rather like that. If you can afford a Tesla, and I'm looking at some of the entrepreneurs around the audience, then really, if you can afford a Tesla, you should be able to afford to wrap it. I can afford the T-shirt, not the Tesla. I can afford the leggings, but it's not going to happen. And the ubiquitous face mask that we suffered for 2 years, which, again, many of us wore at COP26 in Glasgow. So the interesting thing is that we have warmed the planet by 1.2 degrees already, okay? And we have seen extreme weather events all around the world. This is just a collation of the best and the worst in 2021. as climatologists, we thought 2021 was just an odd year, you know, one of those years where you just get a cluster. Except then we came into 2022 and that cluster didn't stop. I'll give you an example. So I've already mentioned 40 degrees in London in July. Now, as a climatologist, I can tell you that the peak average temperature for the last 10 years for July is 24 degrees. That's the peak temperature. Now, that is, for an Englishman, a t-shirt weather, okay? For everybody else, you need a jumper, okay? Now, interestingly enough, 40 degrees. That's 16 degrees warmer than it should have been. Let that sink in. That is the extreme sort of weather we're getting. So what about the future? Now, as scientists, many of you go, well, let's have lots of different planets. Let's torture one. Let's double CO2. Let's half CO2. Let's change the methane. Yeah, unfortunately, we only have one precious planet. And guess what? We're already doing an extreme experiment on it already. So let's try not to do any more. So we use supercomputers. And the interesting thing is, okay, these are based on the incredible weather models that we have. They are netted grids around the world. They go into the ocean. They have layers in the land, the vegetation, the chemistry in the atmosphere, clouds. And on the right-hand side is the actual change in resolution of those models. So the first assessment report by the IPCC was in 1990. And as you can see here, guess what? Britain really was part of Europe because we just didn't have the resolution. By, of course, sort of like 2013, Britain had separated. Now, the interesting thing is the science has got incredibly good. Okay, we understand thermodynamics, we understand the chemistry of the atmosphere. The stupid thing is that we still know the same thing, which is you put greenhouse gases in the atmosphere warms up, the land warms up, sea level goes up, you have climate change, it causes impact, people suffer. We know that in 1990, we know that now with the 2022 reports. Nothing's really changed apart from our certainty. So what does the future look like? Well, we were looking at no climate policies. So 10 years ago, I would have been standing here pulling my hair out, what little I have left, going 4 to 5.5 degrees. Oh my word. Now, the interesting thing is because of economics and political negotiation, we've already avoided that worst case scenario, and we're looking at 3.1 to 3.7. If those promises made in Glasgow, okay, last year are fulfilled completely, then we're looking at, say, 2.4 to 2.8. Okay, that's much better than 5.5 degrees, but remember all the extreme weather events we're having at 1.2? So, the interesting thing is the politics, all the world leaders at Paris in 2015 put their hands on their heart and said, we will keep climate change to 2 degrees and, if possible, 1.5 degrees. Because this is the future. The future of climate change is more extreme storms, floods, droughts, heat waves, and wildfires. And actually, let me add a little extra bit to that. In places that they have not occurred before. Okay? So places that regularly deal with drought and flood, they have the societal means to actually deal with them. When they occur in new places, like wildfires in sort of like the Midlands of the UK, we don't have the means to deal with it. This may lead to water and food insecurity. I say may. We actually make enough food to feed 11 billion people today. There's only 7.9 billion of us. But 825 million people still go to bed feeling hungry every night because of lack of this. Money. It's not about food availability, it's about the ability to purchase it. May lead to migration and conflict. May, because migration is an incredibly complicated thing. Most migration is south to south, not south to north, despite the Daily Mail telling us we are going to be swamped by foreigners. Okay? Conflict. We've seen this year that conflict has nothing to do with climate change, and I'd actually say it's mainly about ego. And it may lead to tipping points. So these are the tipping points that climate change experts worry about. There's a new paper out by Tim Lenton's team in Nature, and we are worried about the collapse of the Greenland ice sheet, the jet stream, hence the 40 degrees temperature that we had this summer. We're worried about the monsoons. We're worried about the Amazon rainforest. Now, the interesting thing about their paper is that they said most of these tipping points are not a concern unless we go over 2 degrees. Some of them may occur between 1.5 and 2 degrees, hence why 2 degrees is so important. I hate to say this on camera, but guess what? The Parisians and the French were magnificent, okay? As an Englishman, it hurts, okay? But they were. At the Paris COP, they were brilliant. They negotiated, they were Machiavellian. Oh, they got 196 countries to sign up to basically net zero this century. And I love the understatement. To achieve this will require the complete transformation of energy generation. Hey, that's good for you guys, okay? Industry, infrastructure, and personal behaviors. So basically everything. And the reason being is because of this. This is our emissions all the way to 2021, and guess what? It's gone up. There was a slight little minor dip in 2020. I believe there was a small pandemic, but this is what we have to do to keep to 1.5 degrees. Reduce global greenhouse gas emissions to 0 by 2050. Let that just sink in, because that's a huge deal. Interestingly enough, 80% of the world's economy is already under laws covering net zero. Okay, so we're a long way there. Admittedly, some countries like India is 2070, China 2060, US, Europe 2050. Oh, and by the way, the thing we forget to tell you as scientists, as climate scientists, because we don't want to scare the public, then we have to suck out CO2 out of the atmosphere for the rest of the century, and I'm now going to move on. Okay, whew. So energy, okay, look at the revolution that occurred post-Second World War, okay? Huge increase in energy because of fossil fuels, which are brilliant, okay? I mean, think about it. Kerosene can pick up a jumbo jet and throw it into the air. It can even get an A380 off the ground, okay? Incredible, very powerful. But, side effect, of course, emissions. 80% of the current energy provided in the world is still from fossil fuels. And friends of mine say, well, hang on, what about all these renewables? That's just eating away at the increased demand. It's not taking away that 80% baseload. So somehow we have to replace that by renewables, or I think there's some other energy you're going to be talking about in this conference, okay? And again, there are billions of people that are still in energy poverty. So as you can see, this wonderful diagram shows CO2 versus GDP. What we need to do is take the pink circle down in the bottom left, move those people up in terms of energy supply, and we need to take the blue ones and drop their CO2 down to 0. And again, the emissions are not caused by there being too many people. There's basically too many rich people. So this is a brilliant consumption estimate by Oxfam, and they suggested that the richest 10% of people produce 50% of the carbon emissions, whereas the bottom poorest 50%, or 3.9 billion people, produce less than 10% of those emissions. So we have to remember that consumption, and actually us, because we are all in that top 10%, actually we're probably in the top 1%. We're the ones that are consuming and producing a large amount of energy and emissions. The other thing is, to frighten you, energy demand will double, okay, by 2050. So remember, 80% of it is by fossil fuels now. That has to go to 0, but then we also have to double the amount of energy. One, because every country consumes more and more energy, and also because there are billions of people we need to lift out of energy poverty. So that's the challenge. Can we do it with solar? Can we do it with wind and tidal? No. Can we put in nuclear into that? Yeah, a little bit. But again, we need an energy source up to 2050 and beyond that can actually fill that gap. So I hope that I've been able to sum up for you the challenge of climate change. And I agree with Tim. The two things that we have to deal with in the future is climate change, but also energy security. One of the things I really wish is that the government, in whatever form it was 10 years ago, had actually listened to their experts, including myself, that said, you need energy security. You do not want to be beholden to Saudi oil or Russian gas. Renewables, you own, cheap, easy, lots and lots of energy for the grid. If we'd done that, we wouldn't be in this energy crisis now. I also think that we have to look to the future because we will need a huge amount of energy. Just take one thing away from this talk, which is by 2050, which is actually not that far in the future, we will double our energy demand. And we cannot do it with coal, natural gas, or oil. Thank you very much for listening.
Mark, thank you for reminding us what's at stake and the sheer challenge, the enormity of the challenge that we have ahead of us as we try to decarbonise our energy supplies. Please join me in thanking Mark Maslin again. And our next session leads on from the challenge that Mark has set and explores where fusion will fit into the energy mix. Please welcome onto stage our panellists and your host, broadcaster and author, Stuart Clark.
Well, thank you, Valerie, and thank you to all of you for coming along today and the UKAEA for asking me to do this. It's such a pleasure to be involved and to bring this first panel to you about the Energy Jigsaw. I'm also extremely happy to welcome my panelists. So we've got Nick Hawker from First Light Fusion and Jochen Latz from McKinsey. And joining us digitally from San Francisco, we have Carly Anderson, I hope, who is from Prelude Ventures. So Carly is going to appear on the screen as some sort of like digital overlord for us at some stage throughout. There she is. Hello, Carly. How are you? Right.
I'm doing great. Good morning, everyone.
So I'm going to start with a joke. And it's going to be a bad joke and an old joke because you've all heard this 1,000 times before. And it's that old joke of nuclear fusion always seems to be 30 years away. Nick, is that still true?
Well, I don't think so. So thank you for having me here. I think I'm really excited about the event. I think it's really interesting. There was a study actually a long time ago where I think perhaps the seed of this 30 years away thing came from. It was back in the 70s, a look at options for funding and developing fusion done in the US. And there's this very famous plot actually showing the different scenarios which they had at the time. You know, really hyper-aggressive, as fast as possible scenarios, more moderate scenarios. And they had funding profiles over time. And yeah, these things were saying, we're going to get to fusion power in 30 years. If you give us $30 billion. The problem is that the funding was never really there. So on this plot, there's a line which is called the fusion never line. So if it's this level of funding, we'll never have fusion power. The actual amount of funding has been less than that line. And nevertheless, we've made enormous progress in the field. So there was two really significant results. There's basically two main approaches to fusion. There's magnetic fusion and then inertial fusion. The biggest magnetic fusion experiment in the world is the Joint European Torus Jet, which is at UK Atomic Energy Authority. They had a massive result last year, the highest performance they've ever got from that device. And then in inertial fusion, there's something called the National Ignition Facility, which is over in the US. And they had a big breakthrough result last year, again, the highest performance they'd ever showed. So I think there's a real sense that the kind of the basic science, the fundamental science has been done. We know what we need to do to make fusion power work. It's about figuring out how to do that in a practical system. The other thing which I'd add as well onto this is there's a lot of excitement and interest in the private sector now. And a lot of the different approaches which are out there are kind of capitalizing, building on that basic research and that fundamental science, but then adding in new technologies or new approaches or differentiating things which make a difference and make it easier. So one of the big themes in magnetic fusion is high temperature superconductors. And what would that mean for the design of a fusion device? It basically means you can make it smaller, and if it's smaller, it's cheaper. And then for us, for First Light Fusion, a really important thing is our simulation capability. So, and it's the methods for the simulations, it's the computers we run them on, and we also use an enormous amount of machine learning in the design and optimization process. So we're doing simulations which could not have been done in the kind of inception of the field. So that's the differentiator for us. So I think, yeah, fusion is not 30 years away. It's, I think, 10 years away.
Fantastic. And I mean, very pleasing to hear that, because as we were hearing earlier from Mark, we need better methods of energy generation now. So Jochen, I wonder if you can help paint this picture for us about the future of energy demands. What's driving energy demand? How might that change in the coming decades?
Yeah, we have seen already a first picture with Mark who showed how electricity consumption is growing. And actually we have a slide on that, I don't know if we can show that one, where we can see that the demand for power will increase by factor 3 until 2050. And it's not only because the global energy demand as a total is growing, it's also that when we look into decarbonization, how we decarbonize, the mean of decarbonization is electrification. So for example, it's so much more difficult to decarbonize cars if you wouldn't go for electric cars. So if we go for electric cars, we switch from liquid fuels to electricity. In the same way, building heating will move towards electricity. In the same way, if we go to a hydrogen economy, the hydrogen is generated by electricity. So the share of electricity of the total energy demand will massively increase. And we have looked into this across 55 industries, more than 70 fuels, more than 140 countries for each of the segments into how would decarbonization move forward, what are the levers for decarbonization, and where is electrification the lever. And when you then put this together, you come up with, depending on the different scenarios of how fast we decarbonize, if we go for, even if you go for the current trajectory with a global warming of 2.4 degrees C in 2050, that would be tripling the electricity demand until 2050. And if we go for an even more ambitious scenario, which we all hope for, of the 1.7 degrees C, then this is going to taking a factor 4 on electricity demand. So there's a massive pickup of electricity demand, which we need to cover somehow.
And this seems like a nice time to turn to Carly and to ask you, Carly, about the technology trends that are influencing or enabling this change towards much more reliance on electricity.
Great. Thanks, Stuart. Yeah, it's really been quite dramatic. And Nick touched on a couple of these key points in his first description of what's happening in fusion. Right, simulation capabilities have just grown exponentially, which has unlocked all kinds of things we couldn't have imagined 20 years ago. And things have gotten smaller in terms of chemistry and material science, energy density. Computer chips are smaller, batteries are smaller, capacitors have been able to get smaller. Magnets at high field, lasers, if you can think about it, we've probably miniaturized it. So that's broadly across the technology sector some of the things we see in evaluating early stage technologies. Production costs have come down through automation and innovations in manufacturing processes. And maybe perhaps most importantly, the rate of technology spread has increased. So advances in materials may not be done even within the fusion community. Some of that may happen over in power electronics, in space sciences is something else. I can talk to you from San Francisco and, in the morning, and scientific publications are available on the internet. If you think about what was on the web in 2000, that has changed a lot as well. So smaller and more connected across industries. And within fusion, a lot of the things that Nick talked about around not just magnets and lasers for inertial and magnetic confinement fusion and power electronics. We've seen diagnostics get a world better, both within fusion and outside that sector.
If we stick... Sorry, Carly, I cut you off there, but I was just going to say, if we stick with you just for the moment, because we were hearing about the targets for net zero and how challenging they are to achieve that. But it's not just achieving it, it's sustaining it as well. And I wondered if you could just paint that picture for us as well about the bigger challenge almost of sustaining net zero as we go forwards.
So thanks, Stuart. Also a great question, and one that Jochen and Mark alluded to, right? If energy demand doubles and electricity demand increases by a factor of 3 or 4, how do you meet that demand? And in addition to meeting that demand, a lot of those studies, we talked about hydrogen production, decarbonizing the grid. There are other energy forms of energy consumption that are going to increase. Air conditioning. 5% of people in India today have air conditioning. 90% may need it by 2050. To pick on something else, air travel, one of the fastest growing emission sectors, may or may not be captured in some of these models. Hopefully, maybe in 2060, we all are able to fly around the world in a day or go to space or something even more incredible like that. In terms of managing our waste, in terms of increasing the supply of potable water in the face of climate change, in terms of removing gigatons of CO2 from the atmosphere. The challenge doesn't end in 2050. It will continue. We will have better tools, but it would be crazy for us to take our eyes off of the future beyond 2050 as well.
Yes,
and
absolutely.
we have seen with Mark, right, that we have a big group or a big share of people today living in energy poverty. So if they all move to the level that we see in the Western countries, this will also, after 2050, result in a massive growth also afterwards, right? So there's also a need to further look at the journey beyond this 2050 curve that we're still going upwards, right?
Yes. Thinking about that, Jochen, here's the first of my dumb questions for today. Why can't we just build more solar farms or wind turbines? Why can't we just scale up the renewables that we have to meet this demand?
I mean, in the first place, when you look at the cost per kilowatt hour of power generated, it looks very attractive to go for solar and wind because this is the cheapest power we have, right? But the point is, we don't have them 24/7 available, right? And this is something where we can put storage on top to compensate. But when we look at the cost for that, and we have another slide on that one, here what you can see is the marginal cost for each kilowatt hour or megawatt hour of electricity added, depending on the x-axis, what is the share of solar and wind in the system. And we see that to cover the first 50% of the whole energy system with solar and wind, this is pretty cheap. And this is significantly below 50 euros per megawatt hour. But when we then go to a higher share of solar and wind, we need to increase the storage put in the system because there is less dispatchable power in the system. And if you would go beyond 80% solar and wind, there would be massive storage volumes required. And each additional percent you cover with solar and wind plus the required storage is going to power prices of more than 200 or even 400 euros per megawatt hour. And this is then where, from our modeling, it makes total sense to find some dispatchable power source that can cover this, this tail of this extremely expensive green power if we want to build a fully decarbonized power system. And this is what we need there, a fully flexible, dispatchable power source that we can bring in that's fully decarbonized. And there are several options for that, where we see that a cost per megawatt hour of below 100 euros per megawatt hour is possible, or US dollar per megawatt hour.
Please.
Can I add to that? So I mean, I completely agree with everything that Jochen has said. I just want to put another thing on there, which is about the deployment rate and how fast we can realistically build solar and wind. They are growing exponentially, and we all know a lot about exponential growth now. But there are limits, because there's only so many people in the world, for example. At some point, you'd have exponential growth, and 1 in 2 people would be building solar panels. So it will max out at some point, and it's just massive, massive infrastructure and takes time to build. So analysis that we've done, looking at the most aggressive deployment rates, which we think are realistic, leaves us with a gap, which is unfilled by 2050. So there's even if the cost analysis was not there, anyway, there's just a practicality to it.
And they're even more dry. Sorry, go ahead.
Well, I was just going to pick up on another point, because a few people have mentioned India already, and that's a big problem because they produce a lot of their electricity from coal, and there's a lot of people, and they need a lot of energy, and we need equity, right, for the developing world. And the grid infrastructure in India is not as well developed as in, for example, Europe. And I don't know, I would kind of assume those numbers are probably based on a kind of European, like very connected, very interconnected grid. So I think to get to such high penetrations of renewables, you would need an extremely well-developed national scale interconnected infrastructure, so that when it's not windy there, but it is sunny over there, the whole thing still works. And that's kind of an interesting question for fusion, because an interesting question is, how big is a fusion power plant? And I won't answer that right now, but if you can have a fusion power plant which works in a less connected grid, powering a town or something like that, that could be a really big advantage.
I can only echo your point of where you said there's somewhere a saturation point on solar and wind, and something what we see at the moment already is, I know players who have built 10 gigawatts of solar and wind in the last 10 years, and they're building 20 gigawatts in the next 3 years. So there's a massive uptick, which is required to match this up ramp that we see. However, we see when you currently go to the market and you do a tender on solar panels, you nearly don't get any offers anymore because the market is just too tight. And this is where this will lead to more and more problems, right? And on the global scale, this will, I mean, you mentioned this India topic. On the global scale, we will need to build this out much faster. And when we look at how many resources we need for that, even if you only look into 2030, in 2030 we would need 3 times the number of people doing the construction of the solar and wind parks that we have today. Where should these people come from, right? And this is making a bit visual how challenging this ramp up will be.
So we established then that there is this energy gap that's coming. And I think we're all here today because we hope that fusion can really help towards closing that gap. But in terms of perception, Nick, I wonder if I could turn to you now, because it's always seemed in the past that fusion, a bit like space exploration, has been this big, massive thing that needs huge national and international investment. You're here as a perfect example from First Light Fusion. That's not the case anymore. Private companies are increasingly getting involved. And so I wonder if you could tell us about how the synergies between private enterprise now and sort of national and international endeavours will help with developing fusion.
So, I mean, synergies. First, it's very important to say that none of the fusion companies, the private endeavours, would be here without all of that prior research which has gone on. It is essential, even down to like really simple things. Like I mentioned our simulation capability, but simulations are only as good as the data you put into the simulations. And there's these massive data sets available, produced over decades, of the material properties that we need. All of the private fusion companies are pursuing things which are faster paths or potentially faster paths. That doesn't mean that we shouldn't be pursuing the kind of public funded and big projects as well. And one way to sort of talk about that is risk, but I prefer to talk about like what's explored and what's not explored. You know, the design for ITER, for example, which is will be the largest tokamak in the world when it's commissioned. That's very, very well studied. It's very well studied plasma physics. There's been a huge amount of work on the engineering of the system. So it's kind of very clear how that goes together. If I come to first light, this is a spectrum, but if I come to first light, we're doing something which is completely new. The core process that we're working with, the final state of matter is exactly the same as the established way of doing inertial fusion, but the way that we create that state of matter is completely new. And it's simulation. It's things that we've invented things that we couldn't invent before because we didn't have the tools. But the physics is exactly the same, right? So it's not more risky. It's exactly the same physics. It's just we're in this unexplored new space where there's opportunity to discover things, or maybe we won't discover things, and that's fine, because I'm perfectly happy to have been someone who gave it a go and had a chance to make it happen much quicker. If that doesn't work, then the big laser programs in inertial fusion will still be there, and they will get to a technology via that route as well, I'm sure. So I don't think we're quite in the kind of competitive tension yet. We're all working together to make all of this happen.
Yes, I understand. Now, one of the things that always, it fascinates me, it impresses me, it inspires me. It's how much work scientists can do, just with pencil and paper. And you alluded to it with the sort of the funding graph that you mentioned earlier. But at some stage, real money is going to have to be put into all of these programs. And Carly, I wonder if you're still online, and we can go back to you, because I wonder how much all of this is likely to cost, and what kind of appetite there is in the investment community for something like this, given that the returns are probably a few decades away, maybe. Does that restrict or limit the type of people or investors that want to put money in? Tell us, give us all the dirty financial details.
Stuart, I think that might be the billion or multi-billion-dollar question. And this is something we're going to discuss more at a separate panel, so a quick pitch for that as well. In terms of how much this is going to cost, if you look at the cost of a single power plant, whether that is gas, coal, nuclear fission, we're talking about something in the billions of dollars, right? And that is, from a providing capital standpoint, a tricky thing to do. You can start a software company for the price of pizza. And most of the high-risk capital, and I'm talking like venture and VC, like to invest millions to tens of millions. Larger startups that are generating revenue are raising hundreds of millions of dollars. And how does that get you to not just the first fusion plant, but the 10 or 5, 10, 20 that are going to be needed for that cost to significantly come down? So that's a bit of a challenge. But I think there is a lot of room for optimism. We've seen this huge sea change towards investing in future positive technologies, in addressing climate change, in energy security, and that transition. Everybody's probably seen in this room has probably seen the $5 billion in private capital that went into fusion recently, or has gone in, most of that in the past year or two. So while there are people who, if you look at the straight return profile for the next 5 to 10 years, might get a little bit scared, if you look at what the ultimate size of the opportunity is, it's massive. And there's a decent chunk of investors who are seeing that and saying, well, we can't not be in this. Particularly mission-aligned investors, people who their primary business is energy. We've seen an amazing amount or increase in interest from corporate venture capital and other similar investors in the past 1 to 2 years in the fusion space. And so this is focused on the investor side, but I think as Nick mentioned, some of the designs that are coming out are significantly more amenable to a modular construction, to smaller sizes, to complementary products. And so we've seen much more compelling economic cases for fusion in the past, just year or two. So is fusion funding out of the woods? No, especially not in this climate. And we're very grateful that governments like the UK, like the US, like others around the world have stepped up and are supporting the science. But I think there's reason for optimism.
That's really good. Now it's going to be your turn to ask questions very soon, and we're going to take one actually that's coming online because it's absolutely germane to what we've just been talking about. But I do want to emphasise as well that Carly will be talking in much more detail about the funding for fusion at 12:05 in the Information Age Theatre. But we have this question online, so. Let's see, and we might go round the panel actually for this. And the question comes from Simon Keynes, and it says, adjusting for inflation, the US spent about $480 billion on the Apollo program. Now, the total budget for all the public and private fusion development to date is about $25 billion. How can the fusion community get politicians today to prioritise this work? So, Carly, let's go for you, and then we'll come around the panel here.
Oh, that's a great question. There's so many ways to take it. I think pointing out the opportunity in terms of the size of the industry. The energy industry is $1 trillion industry. So in terms of economic growth, there's an easy case to make there. In terms of job creation, that's something we've seen a lot of interest in from the federal down to the local community level. And also when you consider the implications of reliance on sources of fuel with volatile pricing and other political risks, I think continuing to share and talk about those and do what the fusion community, do what we say we're going to do, is going to move a lot of political folks in that direction.
I understand. Jochen, how would you go about this?
I mean, I think a lot about this is about understanding. I mean, this is a pretty complex topic, right? That we also discuss now about why do we need it in the system? Why can we not do it only with solar and wind, right? And if we cannot do it only with solar and wind, why do we need fusion? Why can we not take hydrogen and CCS and fission? And I think it's a pretty complex topic, and I think it's articulating a very clear story why this is needed. Starting with the story you just had about rising energy demand, it's about with solar and wind, the energy system could work with storage and hydrogen, but it's just a hell of a lot more expensive than having this kind of dispatchable sources in there, right? So what are these sources? Why is fusion the one that has advantages compared to others? I think laying out a very clear story and communicating this in a consistent way across the industry. And then, I mean, communication takes time, right? I think this is what people need to understand and get aware of.
Nick, anything to add there?
I'm going to strike a different tone.
Please do.
That's all right. I do agree with everything that's been said, but I'm going to call a spade a spade. Why did the US spend $480 billion, inflation adjusted, according to the questioner, on the Apollo program? They didn't do it to get to the moon, right? They did it so that they could demonstrate technological superiority over the Russians and win the Cold War, right? We should be working on fusion because of climate change, yes. However, unfortunately, I think many people, particularly politicians, are tired of that message and hear it all the time. How can we, as a community, convince politicians? Why don't we talk about energy security instead, right? Fusion could be the ultimate in energy security. It is possible to drive enough raw material through the gates of fusion power plant so that you could just shut the gates and produce power for 40 years. That is like technologically feasible to do that. How better could it be in terms of energy security? So that's what I would say.
And I think this topic of, you mentioned in the beginning, it's 30 years till fusion. I mean, everyone who doesn't know about this, what's happening recently, and you talk about fusion, it's like, why are you talking about fusion? It's in 30 years, right? So I think there's a lot of communication needed to also get this away. It's a lot about communication.
Indeed. Well, Nick, thinking, I don't know about you, but all this talk of politics and finance makes me a bit queasy. Let's get back to hardware. Technological challenges. What do we need to do to get fusion onto the grid here?
So technological challenges, we need to solve the core physics problem, or rather, I mean, it's very clear what we need to do to solve the core physics problem. We need that working in an affordable system that has a link to a practical technology. And the link to the practical technology brings in not just the physics questions, but the engineering challenges of fusion as well. And there are some big ones. I don't know how much to go into it, but preventing neutron damage, managing the extreme heat flux, producing tritium, and remote handling are all kind of big challenges. There are very, very credible pathways for solving those for all of the different approaches out there, either by a lot of material science research, for example, is a very important theme for magnetic fusion technology. Or, and again, this is where a lot of the startups kind of come in, or the private enterprises come in, avoiding the challenges through design by switching up the design of the way you kind of extract the energy in the core central chamber. You can potentially avoid these engineering challenges. So I think the thing which kind of always I find fascinating about fusion is this incredibly complicated physics and engineering challenge, and the complexity comes because the engineering and the physics are so coupled in some devices anyway. And despite all of these big challenges, actually there's so much scope for invention. You know, there are so many different approaches out there. Magnetic fusion and inertial fusion are completely different in the way that they work and operate, and there's this whole spectrum in between. There's so much flexibility in the approach that is possible. This is why I think we should be pursuing all possible routes for fusion. And I strongly believe that there will be more than one successful fusion technology, you know, working with different methods and different challenges.
Well, we're going to take a next question from online now, but this is the time now when we just start throwing it open for questions. So after this one question, we're coming to you in the room, so prepare yourselves. So we've got a question here from Leandro, and I'm just going to throw this out, and whoever wants to take it, please do. When we speak about fusion, we talk about using its energy on steam turbines. Is there a more direct way to take energy from atoms on fusion, it says?
Well, I'll jump in. So there is, I mean, you can do that. So the kind of energy release, basically, you end up with a hot plasma. Plasma is you know, it's ionized, it's charged, and if you allow that plasma to expand against a magnetic field, working on a magnetic field, you can extract energy directly with, you know, directly electrically from the machine, which in principle that can work. We're not pursuing that. We're not pursuing that because the thing about steam turbines is they work. So I often kind of joke, I want the most boring power plant design I can get. I want one unknown thing in the power plant, which is the core fusion process. I want it to be a first of a kind on one count only. That's the new bit. Everything else just works and is boring. But for next generation fusion power plants, that is absolutely an option, and it could, you know, increase your efficiency, and you could potentially get to much lower cost. I'd also just say another thing as well, because it's steam turbines, and this is another thing which does kind of come up sometimes. You know, will I have a fusion-powered car? Well, a fusion-powered car is an electric car. Right? We don't need to invent anything different there. Fusion is still centralized generation. You know, it's not going to be like a solar panel on your roof or a fusion-powered car. So it's still a power plant somewhere with, yes, a steam turbine, a generator, connection to the grid, and all of that. So that's where it fits in the energy mix, is in that sense.
So anyone in the room have a question? There's a question here now. Do we have the microphone? Hang on 1 second to ask, because if you don't speak into the microphone, our online people will be in the dark.
Thanks. Thanks, everyone. It's a great panel session. It's Malcolm Parry from Hogan Lovells here. One of the great benefits of public funding is that the outputs are open source, and Nick, you made reference to that. It's a great baseline for your modeling going forwards. With lots of different sort of potential siloed private funded investment opportunities out there, how do the private sector sort of collaborate and make sure that the interim technology hurdles aren't just sort of kept as a log jam for other opportunities out there, which might still be a viable solution?
Yeah, I mean, I think protecting the IP is very important, right? Otherwise, you don't get the funding. So, you know, it has to go hand in hand that someone's got to pay for it. What I would say is that there's a lot more advantage, I think, to everyone at the moment to collaborate on shared problems. And I think we all have our kind of piece which we sort of keep to ourselves for our commercial benefit, and pieces which we share. For us, it's the design of the target, which we don't share. But all of our thinking on the power plant design and all of that we do share. I mean, it's again, it's kind of call a spade thing, right? Someone has to pay for it, and if private investors are going to pay for it, there has to be something they get out at the end.
And I think later on in the process, when this more goes to industrialization, there will be a sharing of the IP versus the suppliers, because it's not only the one player who has it, but if you have, I mean, when you look at other industries, you always have the OEM, the first tier, the second tier, the third tier suppliers, and this knowledge will be spread across the different companies. And then if you have a provider of magnets, for example, he can provide the magnets to different OEMs, right? So this is where also the exchange of knowledge across the different private companies will happen.
If I sort of add to that, when we're speaking internally about the pilot plant and power plants down the line, we don't say, and we build the power plants. It's literally in sort of the mission of the teams that we're forming. The kind of mission statement for that part of the business is enable others to build the pilot plant. Because if the whole world is waiting for First Light Fusion to build 100 fusion power plants to suck all that CO2 out of the atmosphere, it's not going to work. We need to work with others to get to the scale we need.
There's an online question, actually. I'll come to you in a second, but there's an online question that kind of follows on from that. You're saying about people waiting for First Light Fusion to do its thing. And it comes from, this is my terrible eyes, Lilia, I think is the person's name. And it's simply this: which approach to fusion, in your view, will be achieved first? So we'll go around the panel. No fighting, okay? So, Nick, let's try and guess which one you're going to say.
Very simple. I think the National Ignition Facility will demonstrate energy gain probably next year.
Fantastic. Jochen.
I mean, there are so many open questions that need to be solved in the different ends, and we all need to see where it will happen, right? I mean, I wouldn't dare to predict.
Very diplomatic. Carly, you're thousands of miles away. You can say anything you want.
Oh, yes, but we have invested in both inertial and magnetic confinement fusion companies who I'm very proud of, and therefore don't want to pick favorite. But I would like to. We need as many shots on goal as possible. So I do, and we see that there are so many people doing great work. I expect we'll see multiple folks hit net gain by 2030, and that's incredibly exciting.
Yes, absolutely. That's the thing. This idea of multiple paths to fusion and different approaches and different ways, it just opens up the landscape. It makes it not feel like one set thing that you're putting all your money on.
Yeah, we just like everything else in energy, we will be limited by deployment rate as well. So there is definitely a market need for more than one technology.
Fantastic. Now there was someone with a microphone here, I think, for the question. Yeah. There you go.
Hi, my name is Hans van Zutphen. I work for McDermott, which is one of those companies who does want to build those 100 fusion power plants. We're doing exactly the same right now for green hydrogen plants. Building them is not so difficult. Designing them is not so difficult. Our focus is actually on integrating the electrolyzers with everything around it, the balance of plant, and doing it in such a way that we can replicate it quickly all over the world. That's the main goal, because all our clients want the same thing. They want to build more, faster than you can possibly imagine. Is the private fusion industry also focusing on that, or am I here too soon? Are you still focusing on getting it to work, and should I come back in 3 years from now?
Well, I mean, no, there's not a functioning fusion power plant anywhere in the world yet, so we're still working on getting it to work. But I would say that now is the time to engage, as a possible supplier into this industry. I'm going to pick an example, which is which we haven't mentioned yet, which is UKAEA's project STEP, spherical tokamak for energy production. The site for that was announced a couple of weeks ago. Big contracts to be won in supplying that, right? So the other thing I'd pick up on is repeating it, replicating it. And all of the fusion startups are all talking in the same terms here. Design one, build exactly the same one again. That's been a part of the problem in nuclear, and part of the reason the costs are high is because it's always a different one. And if you're just building the same standardized thing, then you can get better at it and the cost can come down.
But I think it's a very good point to now think about constructability, right? I mean, design for constructability is a very important point that you now need to address to make sure that what is coming out at the end is easy to construct and to scale. And we see in the recent nuclear designs that this is challenging in some cases, and that there might be changes in the design needed to make it cheaper in scaling it up. And this is something, if you think about it now, that's the moment to address it, I think.
And this feeds in actually to another question that we've had online from Martin, who says, do we have enough people with the right skills to make fusion technology grow at the rate we need it to grow? So any thoughts on that? Perhaps you should be on the panel for this one. So.
I mean, if we want to build hundreds of gigawatts after 2040, we definitely do not have the number of people today, right? I mean, today we are still in the research phase, focusing on the pilots. I think it's something that needs to go on the way that we also in parallel, as I said, for constructability, it's now to think about how to develop a path that makes it attractive and that builds up this community in the same way. And we see it for fission, if we think about the ramp-ups that are happening, that there is currently a lack of capability. But this is because there was a phase where this was not developed. So it's something to on time think about and address, but I would say we are still on a time scale where it's enough time to build this up.
Anybody else? Yes, there was a hand that went up just behind. It's not you yet, sir. It's just behind you. Yeah.
Yes, hello, thank you. My name is Wesley McCullough. I'm with the TÜV Nord in Germany. And we have a history of a focus on safety in industry. How does the fusion industry, or what does the fusion industry need to do to show the public the safety of fusion and to overcome this general perception and public perception of this fear of all things nuclear?
Anyone want to go for that, or shall we bring Carly in?
Well, bring Carly in.
I'll take that one. More people should go on tours of fusion power plants. I used to work in commercial nuclear. My mom loves nuclear power, not because I used to work there, but because they took her Rotary Club around a nuclear plant in Ohio, and she got to wear a hard hat and learn what the different parts are. And now she's a convert. She understands it, and she feels good about it. Also, what Nick and these other companies are doing is just incredible. What JET and some of the facilities in the UK are doing is incredible. The more people that you can get through to learn about them, the better.
Absolutely. If I could do one thing to help in outreach for fusion, it would, when JET stops operating, I would turn it into a visitor centre, because you're absolutely right. Just show people this, tour them around it, make it, put some lights on, make it look a bit more science fiction, and then people will be sold. So. Now, we are sadly running out of time. We've got probably time for one more quick question from the floor. Yes, you there, sir.
Torlin, your fusion. I have one question. So it's great to have all these companies which say that we have fusion in 10 years. That's fantastic. And I think it's really great that all the companies are thinking out of the box, coming with new approaches. But we have one problem, that's the tritium. So many of the companies, they assume that tritium is around. In the world, there's about 25 kilograms of commercially available tritium. Most of that will be used by ITER. So if you're selling a fusion plant, you also need to basically breed your own tritium. And I don't see companies really working on that. So my question is to the panel, how do they see that? Because it's great to have a working plan, but if you don't have the tritium, you're nowhere.
Can I
Please
pick up on that? Because I sort of mentioned this, skirted over this before as one of the challenges, producing your own tritium. So, I mean, I'll give you our answer. So, we use what's called a liquid first wall concept, which basically means we have the coolant which takes the heat away. Instead of flowing outside the vessel, it flows inside the vessel. And that coolant will be liquid lithium. And this is the way that all fusion approaches produce tritium. So the fusion reaction gives out a neutron. The neutron goes into the lithium. That has another reaction which produces tritium. And you have to close the fuel cycle and kind of bring that back round. It's not as big a challenge for us because of the nature of this liquid first wall system. We're not the only ones who have this, by the way. Other startups have the same approach for liquid first wall. It makes it pretty easy, really, to get above a tritium breeding ratio of 1, get to a higher tritium breeding ratio. So the kind of core physics of it works. We've also been looking at the tritium extraction systems as well. So we're doing some work at the moment on designing a tritium extraction system for liquid lithium. It's complicated engineering, but it's definitely doable. They're all basically different variants, mainly different variants of pulling it out of solution with vacuum in some sort of way. And it looks like we can get good single pass efficiency even with very low concentrations of tritium. There's lots of work to do, but that's my answer. That's our answer.
Well, sadly, we've got 6 seconds left. So thank you all so much, and online as well. And of course, a huge thanks to my panel. Carly, thank you so much indeed. Nick, Jochen, this has been an absolutely fabulous, I think, overture for the beautiful symphony that you're going to hear during the rest of the day. So thank you all so much.